So section 4.3 covers maxima and minima. So when we're given a function, we're often interested on what its graph looks like. That's what I am primarily interested when I'm given a function. I want to know what that function looks like. So for example, some could be like, when is it positive, when is it negative? We might also be interested in what the smallest and largest y value functions are. For example, what if I have y equals x squared plus 3 over negative infinity to positive infinity as my domain? It's important to note that absolute extrema doesn't refer to absolute value, and absolute extrema can be negative, positive, or 0, and a function can have both absolute max and min, just one or neither. So let's take a look at this function. As x goes to positive infinity, f of x, this function, goes to positive infinity as well. So the function doesn't have a largest value. We would say that this function doesn't have an absolute maximum. But what we could say, but what we could say is, I need more room. Given f of x equals x squared plus 3, since x squared plus 1 is greater than 3 for all x in the real numbers, and x squared plus 3 equals 3 when x equals 0, the smallest value, 3, is when x equals 0. So 3 is the absolute minimum of f of x equals x squared plus 3. And we call these absolute extrema. Now let's go ahead and look at this graph so we can understand why its minimum value is 3. So I have x squared plus 3. That's my function, right? When x is 0, y is 3. When x is 1, y is 4. When x is negative 1, y is 4. When x is 2 squared is 4 plus 3. It's going to be 7 all the way up here. So here I have my parabola. Maybe I should have done that a different color, huh, gang? So here I have my parabola. And it goes on and on forever into infinity. So it doesn't have an absolute maximum. But this 3 right here, this is the lowest value it can ever take on. And that's why it's its absolute minimum. So here's the definition of absolute extrema, right? We have an absolute maximum, absolute minimum, and both of those are absolute extrema. So here are some types of extrema. So here we have a cubic function. It has no max and no minimum. Here we have a rational function. Its highest value is 1, so that's its max, but it has no absolute minimum because it keeps approaching 0 as it goes to negative infinity and positive infinity. Here we have our cosine, and if we break it up, because it's periodic, by pi, it has absolute minima and absolute maxima. Here we have a piecewise function. Those are our favorite to graph, aren't they? So it has an absolute maximum at 2, but there's no absolute minimum. And the reason there's no absolute minimum is that's an open hole, right? That means it's not included in the graph. So what's the number closest to 2? It's not 1.9, it's not 1.99999. We can't state it, so there's no absolute minimum. And the rest are pretty straightforward. So I suggest we go through, talk about the extreme value theorem. So the extreme value theorem states that for any continuous function, so it has to have no discontinuities whatsoever, right, over a closed bounded interval, so it cannot go to positive infinity or negative infinity. there's going to be an absolute minimum and an absolute maximum. This is and an absolute maximum. This is the extreme value theorem. It's very extreme. We also see that a local maximum C exists if there's an open interval containing C that's in the domain of f of C, which is less than f of x for all x in the interval. And we call that a local minimum or a local maximum for a local extremum. So here we have, if we look at this function, that the absolute maximum value of our function occurs at x equals 2, right here. But it has a local maximum at x equals 0 because the value of f of 0 is larger than f of x for all values close to it. So if I took a tiny interval from here to here, like here's my a and here's my b, then this, where it's the highest, would be my local maximum. Similarly, the function doesn't have an absolute minimum, but you can see that if at x equals 1, if I took a little interval here on x, this is where its value is the lowest. So there's its local minimum. So it's important to also know, though, that for this critical point here, that at x equals 2, our derivative doesn't exist. Since the function has a corner there, like we can't take a derivative at a corner. The function has changed. So in fact, f has a local extremum at that point. C, the derivative, must satisfy one of the following conditions. Either the derivative is 0 or the derivative is undefined. Such value is known as a critical point, and it's important to find extreme values for these functions. And those are also defined in critical points and Fermat's theorem. So here are some types of critical points. So here we have our 0, undefined, right? Because the function's changing. Here it is undefined, as is here, because there's no local extremum. So those are the different types of critical points. So let's go through an example. I have 1/3 x cubed minus 5 over 2x plus 4. And this is going to be defined over negative infinity and positive infinity. So let's take its derivative. F prime of x equals x squared minus 5x plus 4. Okay, so I need to find where f prime of x equals 0. So the first thing I need to do is factor this, and the reason I want to do this. I want to find where the derivative is equal to 0 is so the tangent slope is 0, and we can use these critical points. So I'm going to factor this quadratic equation to x minus 4, x minus 1. So I have a local, that means if I set these equal to 0, I have x equals 4 and x equals 1. So I have my local max, local min at x equals 4, and my local max at x equals 1. And there's no absolute extrema. Okay, let's do another example. I'm going to have to take the derivative of x squared minus 1 cubed. That gives me f of x equals 3 x squared minus 1 squared, and then I have to take the derivative of the inside, which is 2x. So I have f prime of x, because I'm taking the derivative, equals 6x times x squared minus 1 squared. So I set each of these equal to 0. I have 6x equals 0 and x squared minus 1 equals 0. So that means x equals 0 or x equals plus or minus 1. So I have a local and absolute min at x equals 0 and no extrema at the other critical 2 points. All right, let's do another example. I have 4x over 1 plus x squared. I got to take the derivative using our quotient rules, and I will get 4 times 1 plus x squared minus 8x squared over 1 plus x squared squared. So my denominator can never be 0. Awesome, because this is positive. So this function is defined everywhere. So it's defined from negative infinity to positive infinity. So if I set my numerator equal to 0, that's the only time it could be 0. So I have, this is f prime of x. So I'm going to simplify this to 4 minus 4x squared over 1 plus x squared squared. And I'm going to set this numerator equal to 0. Subtract 4 from both sides. Negative 4x squared equals negative 4. X squared equals 1. X equals plus or minus 1. So now if I look at the graph, I know I have a local min at x equals negative 1 and a local maximum at x equals positive 1. Again, I have a cubic function. It is defined over all real numbers. I go ahead and take the derivative of my cubic function. I get 3x squared minus x minus 2. I want to go ahead and factor this function. That's going to give me 3x plus 2 times x minus 1. I set each of these equal to 0. So I have x equals negative 2/3 and x equals 1. This is going to be my local max. And this is going to be my local min.